healthier. So let's do an evasion attack. This is where you, all right, didn't want that. This is, I have to get used to this crazy browser. There, open a new tab. All right. So what we're going to do here is install SecML. Now, by the way, in Google Colab, let me make a new one here. File, move to trash, return to Colab, new notebook. Okay, they're putting in code here, and your code is all in Python. So that confused me, but I looked up, this is a Jupyter Notebook, and you can run shell commands by putting a bang in front of it. So I can do pip install SecML, and then in Python, import SecML, and you can do curl and git, so you can put anything in here. You can get down to, that's why people are saying, she was talking about doing something like putting a Tor node on here, and as far as I can tell, there's nothing to stop you.
For now.
Yeah, that's right. I haven't tried that, but like I said, I did run my Python project, which involved, like port scanning servers and stuff, and it let me do it. So the possibility for abuse is notable. Anyway, so here it is, downloading SecML and all the stuff and installing it. So now I have this thing called SecML, and SecML is the machine learning library for security, which includes the attacks and defenses, a whole bunch of ones developed over the last several years. And as far as I can tell, this whole field started in about 2020. So everything is like brand new. And there are some online Jupyter notebooks with the code for a lot of those. And I thought, well, I'll just link to them, but they're so hard to understand that, like I say, like a mother bird, I'm chewing it up and making it more digestible. That's my contribution here. So anyway, so here we're going to make a data set. We're going to start with some real artificial data. We're just going to put dots in a plane and sort them. So make a block of code here. This creates 2,000 training dots and 250 test dots. And it should plot them out so we can see them. Okay, there we are. We now made 3 colors of dots in different regions, and of course we're going to try to sort these into categories. So once you have a dot, decide which color it should be. This is sort of a generalized synthetic problem. And this is going to use a thing called a support vector machine. And so there's a nice page, An Idiot's Guide to Support Vector Machines, which is what I love. And here's what it does. So your problem is if you have dots and you're trying to sort them, both of these boundaries would work fine, sorting 100% of the dots. So which one do you choose? Well, the answer is kind of obvious. You choose the one with the broadest lanes between them. That would be the best. So if it's a highway, you have not only this sorts them, but I could move it this way and it would still work, and move it that way and it would still work. So I choose the one that makes the broadest region between them. That would seem like the most logical, and that's what support vector machines do. So here you train your SVM model. All right. And here you can, I missed some code. I'm not going to, I better do it because I won't be able to demonstrate things otherwise. I get the whole thing. All right. All right, the best training parameters, accuracy. This is 98.8% accurate. Okay, now we can visualize the results. Another block of code, okay. All right, so now it has sorted them this way, and you see it gets a few of them wrong. There's some green dots in the red region and so on, but it pretty much works because this data doesn't really overlap very much. So now, let's try an evasion attack. So I've trained it to identify animals, like pandas and stuff. Now all I do is I add a tiny bit of random noise, so there's just a little bit of fuzziness in this image, and you can't even notice the difference, but it's enough to fool the machine learning model that now this is a given with 99% confidence. And this is because, remember, you didn't tell it, find a curve, find a border, find the shape of an ear, find a nose. You didn't give it human understandable steps, which would be more predictable. It did machine learning on like a sample of 1,000 images, so it chose something. You don't know what, and combine that data, you don't know how, so you can carefully train the evasion attack to punch it in its vulnerable spots. The evasion attack tests it and finds out, this pixel affects it by a high percentage. So if I change this pixel by a little, that would greatly change it in judgment, even though a human wouldn't make that mistake. So now you can perform an evasion attack here with the attack evasion PGDLS model. There are different mathematical models to deduce the most effective way to poison the images, and this is one of them. And when you poison it, they're going to poison one dot. I'm going to take one dot and move it to the position that will poison the model, perform an evasion attack. So this one, I have to move it all the way up there to get it to be wrong. Anyway, now here we're going to see how much it degrades under various attacks. We try the maximum perturbation. We're going to vary the maximum amount I can move a dot. So you change the perturbation level, and now you can see how quickly it fails. So this is how far you move the dot, and this is how wrong it is. So if you move it by 0.1, the accuracy drops only a little, but if you move it by 0.5, the accuracy drops a lot. So this is logical, and you can now rate your model by how much perturbation it can tolerate. So that's one way to rate it. And there are various ones to try here. Move a different point and see where it goes to the optimum point. And then move the clusters. Way back up here, where you define the data, here, this is the centers, -2, 0, -2, -2, -2, and 2, 2. These are the centers of the colored clusters. So you can change these numbers, and you can change the standard deviation, and you can make samples that are less separated and more blurry and stuff like that. So that's what you do down here to get some of these flags, is make data that is different levels of confusing, and then see what the best poison attack is on it. And you can change the noise and so on. So there's several variations you run here to see how much the evasion attacks are affected by it. And then we can go here and do an evasion attack on the MNIST data set, which is those census numbers. So we download the data, we select some samples to use, training set samples, validation set samples, and test set samples. And now we view the samples. You see here they are, the 5 and 9. We're only doing 5s and 9s, so here's some 5s and 9s that are identified. Then we train a classifier, and the classifier is 93% accurate. And then we perform an evasion attack. So we're going to take 25 images and modify them to make them misunderstand them. There's different types of perturbation, which I didn't understand. And then you have the maximum perturbation, number of bounds of the attack space, and so on, and a bunch of parameters here which are related to how much it's going to move the test data. But what's most useful to me is just view the images. And here they are. This is the original image that's evaluated as a 9. Here's the image that now it interprets as a 5. You see it's put a little bit of ghostly stuff around the edges. Now it looks like a 5. All these red ones are misidentified now. So all these are poisoned successfully, and you can see it didn't take much poisoning. A little there made it a 9. This one turned into a 5, and I must say that's not very impressive to me, why that turned into a 5. Just these little ghostly dots. Like this one turned into a 9 now. By putting a little gunk there, you can see, this is the thing. Machine learning models, when you say, why did you make that judgment? It's not easy to answer that question. In fact, there's a whole field of research of trying to come up with human understandable reasons why it makes the judgments by analyzing the data partway through, which I thought is familiar because I used to do brain models of the computer and study human vision, and it's exactly the same. You can put a probe in a brain and say, this neuron fires when you see a rat. But you can say, how did it take the pixels and turn it into a rat and activate that neuron? And we have theories. This part of the brain does that, and this part of the brain does that, but we're pretty much making it up, and it's pretty much bullshit, just like this. And the fact is, a neural net is complicated. All the neurons work together to produce the output, and you can't say this neuron did that job and this neuron did that job, not except in a sort of vague general way. So asking questions, which is the point. Now we're going up before Congress, right? And they're saying, your thing is racially biased. This image recognition on faces gets black people wrong. Fix it so it quits doing that. And they're like, well, and they say, why did it do that? Find the code that made it do that and fix it. And they're like, we can't really tell you why it did that. And we can't really modify it and say, there, now it's not doing that anymore. I know that seems to you like we should be able to do that. You made it. Why don't you make it better? It's like, well, we're not really in control of it. It's like you had a baby and the baby starts doing stuff and you don't really control exactly why it's doing stuff. You can try to train it to do better, but you can't really promise it's going to work. That's where we're at. So anyway, there's various options here. You can make smaller predictions and different perturbation types and play with them. And I thought that was pretty interesting. And then there's more poisoning here. You can poison the labels. You can poison by gradients. Let's look at that one because I forget what that one's about. Poisoning labels you did before. Here's where you poison by gradients with SecML again. You get a data set consisting of 3 groups of points in a plane, this stuff again. I guess 2 groups in this case. And then you train the model and you visualize the results. So here it is, it's determined a border, things on this side it calls red, things on that side it calls blue. Now you can do it's gradient descent, which is what I talked about before. Gradient descent is where you have a function that measures how successful your poisoning is, and you just move it to make the poisoning more and more and more effective, sliding down the minimum to find the minimum. That's gradient descent. And so here's another example here, and you can now plot a sort of heat map of how effective various adjustments would be. Moving it over here would have more effect than moving it over there. And you can measure the performance of the poisoning model in various ways. So here's the original classifier that worked. Here's the poisoned classifier, where what you did was move this one dot, which is the star. And moving that one dot twisted the model. Changing this dot to blue when it should have been red caused it to curve around here and change the curve. So you can see how much poisoning a few of these dots changes the behavior of the model. And that's, the accuracy of that sort of attack. So and you can poison the MNIST data set and so on. So that's poisoning. And the other thing I want to show you is really, I think, the punchline. Like I say, it took me a week to get this working, is the defense against the poisoning. This is, if you submit a FCON talk, I thought this was great. They say, if your talk is about an attack, what's the defense? And what's the attack that punches through the defense? And if your talk is a defense, what's the attack that punches through your defense? And what's the defense that will stop it? Because that's the way it is. The cops get bigger guns, so the crooks get bigger guns, so the cops get bigger guns. So this is the attack, and here's the defense. So let me make another separate video about that. Stop this.